So what Manan is actually telling is that, okay, he doesn't have a mic right now. Okay, so what Manan is actually telling is that there were four images of the same star, but due to gravitational lensing, we can actually see those four images. Earlier, we can see only one image. So the deflection and that's JW, telescope actually captured that image. So the image that you can find it on JWST gravitational lensing, that is basically caused because the light is deflecting from the back, and it is showing the four different images. So thank you, Manan, for putting this. That was really good. Okay, so now we step into something very serious, that is, what is a system. Now, why I'm trying to go a little step back and explain what is a system, because most of the people, they directly go into general theory of relativity. They go into the tensor mathematics, calculation, differential geometry, without understanding what is a system. The basic objective of making you understand what is a system is that I want to show you a very deep, I would say, a very deep understanding of the difference between a classical system and a quantum system. You need to understand that first. Second thing is that I will also show you that why we call general relativities as a classical system. Now, I might ask me, sir, why are you talking of quantum mechanics or quantum system? No, I'm not talking of quantum system. But what happens that, say, for example, if I want to say to maybe Prashant, see how beautiful this how beautiful this room is. It is full of light. So Prashant might say, okay, sir, we all know. But say, for example, Prashant is in a dark room, and then when the light comes up, he will say, really, sir, you told that the room is so bright. So until you know the opposite side of general theory of relativity, which is the very small, you won't be able to understand the very big. Okay, so that is basically what I wanted to understand. So we start with this, which is called what is a system, and I will try to make you understand what I'm trying to mean by this. Okay, so you see, when we talk of a system in general, we say that it is coming from the Greek word systema or systema, whatever. It means that it is a collection of objects that are interacting with each other. Now, I am not boasting, or this is not my ahamkar that I'm telling you this, but this is something which is not being taught in general mathematics or physics classes. We the students and the teachers, they go directly into the mathematics, but this is something which is very important to understand. And maybe Rajagopalacharya sir, who is a very senior engineer over here, maybe he can throw some light also. So I'm trying to first of all define at a very basic level what is a system. There is a reason for that. Hold on, then you will understand. So now see that, so for example, if the ball is rolling down, right, we can create a simple system consisting of a ball and a smooth surface. And if we study the system, we can learn the law of physics, that if the inclination is too high, the ball will roll faster, or whatever be it, right? So what I'm trying to say is that a system in physics is a collection of objects that are interacting with each other. The main concept over here is that it is a collection of objects which are actually, you mentioned that in quantum field theory bends the light curvature. Yeah, I will come to that, Faraz. Let me first go ahead with that. I will answer all your questions, don't worry. So the thing is that it should be basically a collection of objects, and those objects should be interacting with each other. It can be gas molecules, it can be chemical molecules, whatever, and we call it as a system. Okay. Now you see here, say for example, in a system we call mechanical system, thermodynamical system, electromagnetic system, and dynamical system. That means there are various kinds of a system. Say for example, a rocket which is moving upwards. So it will allow us to make predictions. So if I know the initial condition, that if I throw a ball on that wall, the ball is going to do come back. So that is what is called a system. That is there is this nice prediction, and we can say from that system that the particles or the gas molecules are going to behave like that. Now you might ask a question that what is not a system. Now, for example, on the right hand side, the blue box tells, for example, force in itself, until it interacts with anything, force itself is not a system. Gravitational constant is not a system. Okay, because these are again constant. Speed of light, constant. Reduced Planck's constant, constant. Symmetry, constant. So these are actually which is called not a system. Okay. Okay, am I okay till now? I mean to say, I'm just asking every 44 people. Are you being able to get hold of me? Okay, okay.
Yes, sir.
Yeah, I will
Yes,
keep
sir.
on asking, yeah, from time to time.
Yes,
Don't
sir.
worry, because it is important from me
Yes, sir.
also.
I agree.
Right. Okay. Now you see, in a system in physics, when we are talking about physics, is dipole a system or not? Very good question, Prashant. Well, dipole won't be a system until and unless it actually interacts with each other. Yeah, that is very true. It's a very good question from Prashant. Yes, I mean to say dipole cannot be called a system. I will come to that later, but it's a very good question. Okay, so in system in physics we call there is a three system. One is a classical system which is highly deterministic. I will come to the notion what is deterministic. Another is, or what is called, a relativistic system, and another which is called a quantum system, which is probabilistic in nature. In general, we will divide physics into three systems. Now here there is some also a kind of a misconception. Some people say, what is modern physics and what is classical physics? Okay. Now, modern means an era. Say, for example, 1915 to 2000. This is the time. So there is nothing which is called a modern physics. Modern means modern dress, modern people. It is an era. It is a time. But if we talk of physics as a system, it should be either a classical or a non-classical, that is quantum system. I have divided into three, but actually it should be two. What about dipole in electric field? Yeah, that is what I'm saying, Raja. That let I will come to those questions. First, let me cover up what I'm trying to give. Otherwise, if I keep on answering this question, it will go up till 12 o'clock, and you won't enjoy your Happy New Year. Okay, so so I have divided into three, but essentially it should be two: classical and non-classical system. Okay, so here you see classical system is basically the Newtonian system. Quantum system, you said that system constituents interaction with each other, but in thermodynamics, just a second, where is the chat? But in thermodynamics, please answer question. Yeah, but in thermodynamics, we consider system of gas non-interacting molecules. Yeah, thermodynamics has got its own, I'm going to say system. I'm talking of system as a whole, Nitish. So thermodynamics can also be considered of a system when the gas molecules are interacting. Okay. So, yeah, I will come to those questions later. So, now the special and relativity is basically also a relativistic system, which is classical in nature, and quantum system, which has got a wave function. Now, what we are trying to do is that in order to understand general theory of relativity, as I was telling with an example, that it is very important to understand a relativistic system with a quantum system. Why? We will soon come to that part. Now, I have put up a question mark over thermodynamics. In general, we consider only the macroscopic, uh, we consider only the microscopic and not the molecular level. Yeah. Yeah, absolutely. I think Rajagopal sir has answered. So I would request all of you that we can keep those questions later, because otherwise everything I will constantly go to the question and answer, nothing will be covered up. Yeah. So the thing is that now you see that special and general relativity, I have put up a question mark over here because there is a reason that whether it is a relativistic system or not, I'm going to answer that in the next few slides. Now, here there is a question which is called, is it all about relativity? That means this is very important. Who is joining so late? Palash. Okay. Now, this is a very important question which I would like to talk, is that in general, whenever we are learning general relativity, any one of you, okay, what you will do, you will go into tensor calculus, tensor analysis, geometry, non-Euclidean geometry, etc. The basic idea which is very important to know is that we call it as general theory of relativity. Okay, but I am going to show you, and I'm going to make you understand that this word relativity is not very true when we talk of general theory of relativity. Okay, I will explain to that in a few moments time. Okay, I call it general theory of geometry. I have put a cross over relativity because I don't think, or many physicists or many mathematicians think, that it is more of geometry rather than relativity. Sagardut, are you getting all things till now? Everything is fine? Great.
Yes, sir. Everything.
I
Okay.
am asking is because he is the youngest person and he is reading in class 9. So we should appreciate and pay attention so that he also understands. Right? Very young fellow and very good that you have come up today. Okay. Now look into this slide. Let me zoom it also a little bit more. Uh, Okay, I will just zoom it. Okay. Here you see this is something very important. Now, if I talk of special theory of relativity, I mean to say, because general relativity is what? It is coming from special relativity, right? So, special relativity, you see, there is something which is called inertial frame of reference. There is something which is called speed and velocity. You remember the speed of light is constant, right? It is experimentally provable, and there are a lot of frames of reference, this frame of reference, that frame of reference, all those things, right? That means I can tell that special relativity primarily deals with study of relativity, speeds, time, and space. Now, remember, now we are going into the real aspect of general relativity. So please do pay attention and let me know whether you are getting this point or not. So special relativity actually talks about speed, time, space, etc. And I think Sagar Dut, who already knows calculus, can easily learn special relativity because not much mathematics is required in special relativity, right?
Sir, I wanted to say something. I have actually learned a little bit of special relativity. Like,
Very good, very good, great. Now, if you see, if I move to the right hand side of the slide, it talks of general relativity, which talks of non inertial frame. That means the things are speeding up, it is not in a uniform motion. Number one, it talks of gravity, it talks of geometry of space time, and it talks on a very large scale. That means it talks of what on a cosmological scale, black holes and stuffs like that. So that means we will soon see that general relativity is not a study of relativity as per se. It is more of the geometry of surfaces. And because it is the geometry of surfaces, that is why it becomes exceedingly difficult to understand. I mean, it's a challenging. I should not say difficult, it is challenging. Okay. Now you see all those things. We will cover some of them: space-time manifold, local structure, tensors, Ricci curvature, curvature scalar, geodesics, all of these things. High school kid with just algebra and Pythagoras can easily understand special theory. Absolutely. Rajagopal sir is helping me with answering all the questions. Right. So all those things, affine connection, Einstein field equation, parallel transport, all of them consist of geometry rather than mathematics. The basic idea why I am trying to tell you this is that why anybody who has got an intuitive thinking, I mean to say inborn, who has got an intuitive thinking can understand general relativity much better, because it is all about the geometry, curve, etc. And if I talk of the mathematical mind, that is more in quantum mechanics, because quantum mechanics, it is I would say it is very less to visualize, but you have to be a master in terms of yeah, Rahat, assalamu alaikum, good evening. Yeah, Rahat is also joining from Lahore, and she is actually teaching a lot of specially abled children who cannot see, who cannot talk. So all my due respect to Rahat. So these consist of the geometry. That means anybody, any student, I mean to say maybe Amal or Monica or James, who is willing to learn general relativity, first thing you all have to keep in your mind is that, am I good in geometry? Am I good in visualization? Do I have a intuitive mind? All those things. Good evening. Yeah, Sadat, very good evening. Now you see, don't worry about what is covariant in nature, I will say. So speed of the light is constant through space, but space can move, uh, faster than the speed of light. So can we say speed of light is constant in space? Yeah, absolutely. Space can move faster than the speed of light. No, this is not a right notion, I think. I will come to those questions later. So what I'm trying to tell is that if you see this, the gravitational time dilation, etc., all those black hole singularities, etc., they are very non-linear in nature. Non-linear means it won't move in a straight path. It will move this, and it will accelerate, right? And this is something which is called a covariant in nature. Now, if you ask me what is covariant in nature, just hold on for a second. I will try to uh, okay, let me explain it in this way. Covariant in nature is something, for example, if my body weight increases, okay, If my body weight increases, my blood pressure also increases. Say, for example, if my body weight is reduced, my blood pressure is also reduced. That means it is means one thing is going in this way, another thing is also following it this way. Directly related. Absolutely, Shubham. Thank you. So this is why it is called covariant in nature. And Einstein's general relativity is actually a theory of gravity, which is called covariant theory of gravity. It is called what? Covariant theory of gravity. It's totally non-intuitive. Absolutely, absolutely. Thank you. Yeah. Now here you see this is the difference that you have to keep it in mind. A relativistic effects of special relativity. I mean, so whatever time dilation, twin parallax, there are a lot of special relativity. Now, when it is getting generalized, very generalized into a curved space time, there's a huge mental shift. Okay, so there is from relativity, we are moving to geometry. There is a huge change in mathematics. There's a huge change in coordinates which are being transferred. So teachers like Monica, etc. I have told Monica has participated in the last webinar also. I always tell that whenever you are teaching a subject, whatever calculus, general relativity, special relativity, trigonometry, whatever you are teaching, first try to make your students understand that why you are learning this subject. That means there is a problem with normal mathematics. That is why we want linear algebra. That is why we want trigonometry. So what is the problem? Make the students understand on that. Point number one. Second thing is that what is the mental shift? Mentally, what you need to shift? That means we will be doing with mathematics which is totally related to geometry. That means what Rajagopal sir was telling, that if somebody knows Euclidean geometry and normal Cartesian coordinate can learn special relativity. Why? Because it is on flat space time, right? Which we call Minkowski space time. But remember that when we are moving to general relativity, there is a problem. I mean to say there's a challenge. Challenge is that it is not flat. Challenge is that there is a curvature. Challenge is that there is a geometry. The challenge is that we need to mentally visualize. Otherwise we won't be able to understand. So this is a kind advice to all the teachers who are there, that before going into that, make the students understand, which I do, that this is going to come. So are you mentally aware? So if they are now mentally aware, they can learn the mathematics, but don't give them the mathematics first. They will always face a problem. Clear till now? James, are you still there? I mean to say, is things going fine? He's joining from Dubai after that, so I just wanted to talk on that. Okay, so here you see this is the transition what I was talking. Length contraction, time dilation, all those things are now into tensors, geodesics, parallel transport, all those things. So that means it has got a transition from relativity to geometry, and the mental change that you keep it in mind is it has less relativistic and more of the nature of space time. Yeah, Ayushi, you can ask me your question.
So, as you have said that gravity is not a force, then why we used to study about the four fundamental forces like strong
No, no,
force
no.
and gravitational force, including all.
Four fundamental forces are basically four fundamental forces because we are moving towards a unification: strong force, weak force, gravity, and electromagnetic force, right? So these four forces, why we are studying, because we are looking for a unification. Strong force, weak force, and quantum mechanics has already been united by Richard Feynman in quantum electrodynamics. But what is left is gravity. That is why we are trying to find out that can we unite strong force, weak force, electromagnetism, and gravity, all of them together. So that is why we are studying gravity. It is not that I would say that it is not because it is a not a force. It is already understood that it is not a force, but how we can unite gravity, electromagnetism, strong and weak, that is what we are trying. Okay. If that can be united, then we can, yes, you're absolutely right, we can get a theory of everything. Okay, so here it is quickly to understand that we are now moving into a mathematical realm where we are going to understand about curvatures. So anybody who is very intuitive in mind can understand that, and it will basically deal more with geometry rather than simultaneity or relativity. Okay, so till now it is 25 minutes we have started. Everything is okay with you, Sagardu, Satyamev, everything, Manan,
Yes, sir.
everything is good? All
Yes,
of
sir.
you are
Yes,
getting my
yes,
point?
sir.
Okay,
Yes.
okay.
Yes,
Now we will
Satyam.
try to understand what is a classical system, because we need to first look into what is a classical system, and then from here we will move to understand that why general relativity is that. You can tell, okay, Shaunak, general relativity is classical, Newtonian is classical. What do you mean by classical? You have to be mathematically and physically, you have to tell what is classical system, right? It is not because these people were old, Newton was 400 years and Galileo even that is why they are classical. That means, Shaunak, I have also have got my hairs white, that means I am also classical. Or Raja Gopal sir maybe even classical. No, not like that. So we really need to know what is a classical system. Okay, so first of all, we need to understand that classical system is actually a systematic way. No, I will come to that, Sadat. So first of all is that these are actually very deterministic. Deterministic means that if I repeat the experiment same and same and same and same, it will give the same result. That is one. Okay, so it has a set of rules, and it is in logic, and it is reversible. Now reversible means what? That means if I throw a cup on the floor, it will break, but the laws of physics also tells that these cup can be reversed with time, and it can get back the original cup. I mean to say physically, I mean to say it is not practically possible, but it is called a time reversible system, isn't it? For example, something like that. So if anything is there which is happening right now, if I put the equations back, hypothetically it will come back to that system, right? So it can predict the future and how the events will be. Yeah, it's just that first one does non-consider. Yeah, absolutely. Great. Yeah. Now here you see this is something very important. Now say for example, I have got a coin. It is like the Hindi film Shole's coin, which has only got a head. Okay. So now if I toss the coin up every time, what it is going to harm, you will always have a head, right? So this is called a single state system. Okay, so here you see I have got a closed system which has got a magnetic charge, photons, etc., and it does not exchange any matter with its surroundings. That means it is in a closed kind of a system, right? And if I throw the head every time, Amitabh Bachchan will always tell that it is coming to head, because the future is got only one state space, which is the heads. Now here you see if I get a head and a tail, then how will the system evolve? So from head I will get tail and HT, and if I start with tail it will be TH, right? Now also there is something, if I get a head and if I constantly come back to head, then I will have HH. I have not explained because this will again take some time. This is called the law of conservation of energy. That means, I mean to say, deep there, what we told energy cannot be replaced, not destroyed. I mean to say, that is what the law of conservation. But in a classical system, if you say, if it is a state, then it will always go back to that state. That means it is neither created nor destroyed. That is what I explained in one of the shlokas of Gita. So it is going back. So this is what is called the law of conservation of energy. And if the system evolves with time, so T1, T2, T3, things are changing, that is called a dynamical system. Clear? Okay. Now here comes the exception. So if a dynamical system must also be reversible, which I told, say for example, you see the box 1. So if I'm standing at box 1, I can go to box 2. From box 2, I can go back to box 3. And from box 3, I can come back to box 2. So on box 2, what my past is what? 1. What is my future? 3. And from 3, I can go back to 2. Present, past, and future, typically a kind of a classical system. Now try to imagine that you are suddenly at point number 2. Suddenly, I mean, this is out of the blue, you are just at point number 2. Okay, so what will happen in that case, point number 2? Then if I ask you, okay, Sagar, to tell me what were you, Sagar won't be able to tell me, because he is suddenly at point number 2. There is no past 1, there is no future 3, right? So classically we should say there must be one arrow to tell where you are going and where you came from, right? But if a system is irreversible, we say that it is just at point number 2. That means state 1, I have got no past and I don't know where I am going. This is called, which is called a time irreversible or an irreversible system. Okay. Now here I would like to tell you, here I am taking a shift now to a quantum system. Now you see, in typically in kind of a quantum system, the left hand side graph is the classical system. So I know 2 and 4, whatever. But in a quantum system, the electron can be there. I don't know. I really don't know. Why? I will come to that later. And it is denoted by this wave function psi. And when I square that wave function, yeah, I will come to that later. Yeah, definitely. When we you can get those things. When we square that part, we get a probability density. That means that in this area, there is a probability that the electron might be there, but we cannot tell it for certain, right? So it is a probability distribution over a certain area. Yeah, probability distribution with respect to position, that it might be there, but we are not certain. Now, here I would like to give you a quick example, what is called a spontaneous emission. Now, I am trying to relate quantum mechanics with general relativity. Why? I will tell you. This is called spontaneous. What do you mean by spontaneous? Spontaneous means suddenly it happens. It just suddenly happens, right? So, fireflies, neon lights, all these are spontaneous emission, right? So what happens is that when a particular photon or a subatomic particle, it transits from an excited state energy to a lower energy state, it emits a quantized amount of energy. Quantized means certain amount, only this much, say 5 millimeter or 10 meters, right? Without any driving force. Absolutely, Satyamev is absolutely, you have got a bullseye. So this process actually occurs in naturally around us. Now here comes the difference, mind it, what I am trying to take, quantized amount of energy. That means quantum mechanics tells that only this amount of energy is possible, whatever, right? But classical physics, what does it tell? Infinite amount of energy is possible. That is the clash. Classical physics draws those infinity plus to minus infinity, and we do an integration. But quantum mechanics, we cannot do that. Now, here you see spontaneous emission, for example, this one, for example, fireflies, neon lights, all those things cannot be explained by general relativity or classical physics. Why? First of all, classical electromagnetism, not quantized. Quantized means that try to understand that it is just this much. Although there is a other canonical quantization, etc. I will come to that later. Classical electromagnetism cannot be quantized. Why? Because electromagnetism is something which has got an infinite source, infinite energy, etc. Just a second. And in the absence of the quantized electromagnetic field, the excited state of atom cannot go back to the ground state. That means here is the atom, it has been excited, okay, right, from this, and it is not being able to go back to the state. And in order to explain spontaneous energy, we need that this space from this point to this point, if this is the point where the atom has been emitted, so from this point to this point, this entire space needs to be quantized, which I am unable to do, because classical mechanics does not give me that tool that I can point quantize every point in space. So that is why spontaneous emission is called an irreversible process. Now you see the two differences. You saw that I told that Sagar is standing in front on position 2 and he does not have a present or a past. That means spontaneous emission is an irreversible process because it is spontaneous. It is quantized. But on the other hand, classical system is a reversible process because from 1 I can go to 2, from 2 I can go to 3, from 3 I can come back to 2. Are you all clear? Are you getting me what I'm trying to mention? All of you. So
Sir,
that is,
Yes, sir.
yeah,
I just
yes,
got
sir.
a small doubt, sir. You said classical system, the process is reversible. But in the real, say, thermodynamics, heat engines, the practical ones are all non-reversible.
Absolutely.
So
I mean to
how
say
do
what,
we?
yeah, I mean to say reversible in the sense that if we put the equations back, hypothetically, we can go back to
Okay,
the original state.
okay,
Yeah.
okay. You're talking mathematically they're reversible. Okay,
Mathematically, they are reversible. Right.
fine.
Absolutely.
Thank you.
Yeah. Won't that mean decreasing entropy? No. Again, entropy is something, Shubham, which cannot be totally explained in classical physics. Entropy is something we need to define in terms of quantum physics. So there is a decrease in entropy won't happen. That is time reversibility. Entropy classically is difficult to define. We have to use quantum mechanics for that. So this is the difference between classical and quantum system. Now, why I am telling this slide will make you understand. You see that is like a function where we check for every value in time. Absolutely, Sagar. So we understood from classical to quantum how things goes, right? Now you see in general relativity what is happening. Pay attention to the right hand side corner picture. If we are given the initial conditions, it can be mass, it can be energy, it can be anything, we can predict the future, right? But this is not happening in case of a quantum system, because quantum is something very spontaneous, and we cannot give an initial condition, and we cannot predict the future. Why we cannot the future? Because of this slide, this one. Because I really don't know where the electron would be. It can be here, 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 here. So how will I predict the future? So this is actually what tells the difference between classical system and quantum system, and why general relativity cannot define, or any classical system cannot mention a spontaneous emission. And it is all because that the future is very unpredictable. God does not play dice against quantum mechanics. Absolutely. Yeah, absolutely, Rajagopal sir. And I will just tell you, Rajagopal sir, that I made a complete video I will pass on to you. Please do connect me in WhatsApp on the philosophical implication of God does not play dice. And the original paper, I think you will like that video. Okay, so this is the basic idea. Now, also, I would like to tell you, which I cannot because the restriction of time. Remember that Schrodinger equation, okay, is a classical equation. It is not a quantum equation. Okay, it actually tells that the kinetic energy and potential energy, just the total energy it calculates. Okay, it is something which is equal to F equals to ma. If you want to know more, I have done a mathematical derivation using Newton's second law of motion to show that Schrodinger's equation is highly classical in nature. Now, you might ask me a question that then is it something which is not related to quantum mechanics? Yes, it is definitely related to quantum mechanics, but it was another person whose name is Paul Adrian Maurice Dirac.
Dirac.
Yeah,
Dirac,
Dirac
yeah.
actually used this equation in order to make it as a relativistic equation, which is called the Dirac equation. And I remember the famous, my favorite line quotation of Dirac, that you pluck a flower on the earth and you move the farthest star. So if you just pluck a flower, it will move the farthest star. That means how beautifully everything in nature are connected to each other. So that is the limitation of Schrodinger equation, that it was not relativistic in nature. Don't think this psi actually means that it is, very much relativistic. No, it is not relativistic. It is probabilistic. But in order to make it relativistic, as Rajagopal sir is telling, we use the Dirac equation. So up till now, what we tried to prove is that what is general relativity, what is a classical system, what classical system can do, and what quantum system can do, and that is why general relativity is very classical in nature. This is one video which you can look into my live lecture, the importance and significance I have done. So now we come to the central part, that what is evolution of special relativity. I mean to say how special relativity, I won't take much time, I'll just go over these parts. So this was the miraculous years, we call it annus mirabilis, right? When first paper was on E equals to HF, second paper was on Brownian motion, third was special relativity, and the fourth one, which, yeah, okay. So, yeah, absolutely.
I have this book.
You already have got those book.
I have a long
Uh,
lot. 20 years
okay,
back.
okay, okay, great, great. So that actually speaks of what special relativity, etc., are all about. So these are the four papers actually which changed everything in terms of our understanding of physics and mathematics. We go to the next part. I just want to quickly skip over this. So it was during that time, it was the presence of ether which was actually being shattered by Michelson Morley experiment, who told that ether does not exist. Constant speed of the light is based on, absolutely, 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 Sagar, you are absolutely right. I will show you that. Okay, now one thing people might, they do not know is that the Lorentz transformation, what we talk of today, that it is Lorentz, yeah, luminiferous ether, it was actually discovered before Lorentz by this famous person whose name is Henri Poincaré. We do not call it Poincaré, but it is Henri Poincaré. So Henri Poincaré's group, which is called the Poincaré group, actually discovered what is called the Lorentz transformation or Lorentz invariance principle. But as you know, history never remembers Henri Poincaré. He's mostly remembered for what is called the Poincaré conjecture, which was later proved by my. I keep his picture in my wallet. That is Grigory Perelman. I don't have the wallet, but I am a crazy person. I keep two pictures in my wallet along with my cash. One is Kurt Gödel, and another is Grigory Perelman. These are my two gurus, which I keep it on my bed when I go to sleep. Anyway, I hope you won't mind. Yeah, so these are the two. So that is how it came upon. So the motivation why Einstein formulated special relativity is that Sagar, a very intelligent boy, told that Michelson-Morley's experiment has told that there is no ether. So if there is no ether, that means light is traveling at the speed of light at a constant speed. Number one. Second thing which also came is that it was not clear if the speed of light is constant, then electromagnetism is also related with light, right? Then how electromagnetism or Maxwell's equation can be framed in a new way? Okay, are you all getting my point? Muhammad Azam and Rajendra, I mean, so those who are not interacting with me, I can see only three cameras on me, Rajagopal, Monica, and Sagar. So, are you all getting me? Can you
Yes,
just tell
sir.
me yes or no? Okay. So,
Yes, sir. Yes, sir.
yeah, inconsistency. Why there is inconsistency? Because how can electromagnetism be actually taken into account? Because remember, history says that even Maxwell framed the electromagnetic equations keeping in mind ether theory long back, right? And the experiment has already proved that earth movement, there is no ether. So that is the real motivation. The first is that if there is the speed of light is constant, then how can we frame the laws of physics? Second, if it is constant, then electromagnetic theory, how it can be proved? Okay, here we come. This is what 2024. So how many years? 1905. Sagar, can you calculate? So we are going back to 1905. Let us wear our jacket because it is quite cold in Bern. It is in Switzerland, and we find the desk of Albert Einstein, where he actually formulated the world's best theory, that is special relativity. Okay, and I always tell to my students that you see here there was so much of disturbance, right? Because it was a very, I would say, a very cloistered place. But you see, nowadays young people say that I need an air condition, I need yeah, 1887, apparently Einstein. Yeah, absolutely. And we need a quiet home. There should be no television. Parents should not be talking. No mobile phone. But you see, during that time when there was so much amount of noise, instead of that, Einstein told that I hatched, as if he is a bird and is giving birth to the eggs. So I hatched the most beautiful ideas. Okay. So what do we see in special relativity are two things. Legend. Yeah, absolutely. That the laws of physics are same, and we will come to that. Don't worry, I'm going to explain it, because if you don't understand why space and time are now united, you won't be able to understand general relativity. And second thing is that the speed of light is obviously constant, proved by Michelson-Morley's experiment. Okay, now pay a little bit of attention here. Now if I'm sitting right on my chair, right, I can feel a weight, isn't it? I can feel a weight. My feet is right on the ground, right? I'm feeling a weight, that there is a up thrust. Okay. Now my college is located at the 14th floor of a building, right? Every day when I move up, believe me, I'm telling a true story. Every day when I take the elevator, I think that this is what Einstein thought every single day. So when I am sitting on a chair or on a table, and my legs are exerting a pressure on the earth, I can feel that, right? Ayushi and everybody. Now when I'm moving up an elevator, okay, I'm moving up an elevator, we feel it heavier, yes, and this thing is going right up. That means a pressure which is falling here and a pressure which is given here, both of them are the same. I mean to say, in terms of feeling, you see. That is, the pressure which is being exerted on my feet is the same pressure which my feet is experiencing when I'm moving up the elevator. That means box in a stationary gravitational field is equal to the box accelerating in empty space, taken into consideration that there is no sound, etc., etc., ideal conditions, right? So box in a stationary field is equal to box in an accelerating space. Similarly, box falling freely is equal to the box which moves through a constant space also. Because if today, god forbid, my floor collapses, and this is what Sagar, you told me that this is the happiest moment in my life, happiest moment when Einstein thought that if the floor collapses, then the man is falling, right? And if the man is now falling, how would the man fall when it is out in the space? Same way. So that is why acceleration, gravitation, and falling, all of them become equal. Now, can you get a little bit very deep philosophical sense what I'm trying to say? From from the laws of special relativity, we generalize to geometry. From geometry, we are trying to generalize now gravity. We cannot call gravity as acceleration, this, that. It is the same feeling, it is the same equation. Are you all there with me? I mean to say, can you see a very deep significance which is coming? How deep philosophical it is. That means everything is actually coming to one single thing. Okay. So this is what is called the principle of equivalence. That means a body which is moving, this and this are the same. And now you try to understand one thing, that there is an elevator, okay, a lift, and you are moving up. The elevator is moving up in this way, and a ray of light is being passed. Now, when the ray of light is being passed and the elevator is moving up, it won't go straight, it will bend. It will slowly bend. Why? Because the entire space is curved in this way. Now, I'm giving you another clue. If you stand in front of a seaside, just on the beach, and if you look towards the horizon, you will see a place where the sky and the ocean is meeting. It is not straight, it is a kind of a bulge, right? So that is also what says that space is curved. So if you shine the light, the light won't go, because Newton told that it is a rectilinear movement of light, right? But it is bending, it is going this way, right? All clear, Rajendra and others? Please do respond, yes or no.
Yes,
Otherwise,
yes.
yeah, okay.
Yes,
All of
sir.
okay, great. So this is
Actually,
what.
Professor, I'll just interrupt you for a while.
Yeah, yeah, yes,
You
yeah, sure.
you gave the example of that lift which is accelerating
Mhm.
upwards,
Right,
and a ray of light is coming this and parallel to
right,
the person. So what he is observing in the lift
right,
is that he is accelerating upwards.
right.
Because of that, this appears to go downwards in a curved
Absolutely.
path.
Right,
Had he
absolutely.
been had he been going at a constant speed instead of
Yeah,
acceleration, you would have
it
seen
would
it
have been
going
straight. Yeah,
straight line, but still there will be a shift,
there
which
will
is
be a
what
shift.
in
Absolutely.
special
So that is
relativity we
why,
have that.
yeah, that is why we are talking of the non-inertial. That means it is
Okay,
moving,
it's non-axial.
accelerating upwards. Right.
Acceleration.
Absolutely. So what bends the light? Now the question comes: what bends the light? Because once we have proved that light speed is constant, there is no ether. Then what it is bending? It would have been ether. I would have told, okay, ether is bending the light. So that is why we come to know that gravitational and inertial forces are the same, and it is the curvature of space which is bending, and it is called Einstein's Newton apple insight. Why? Because Newton thought then the apple is falling. Yeah, it is takes the shortest part, and it is called geodesic. They'll come to that, and this is called the Gedanken. Gedanken means thought experiment. That is a German term. Okay. Now we come to a very important and central idea, that space was space, time was time. Everything was going well with Mr. Newton. That why suddenly Einstein would unite space and time together? What was the problem? So here you see all the momentum, motion, torque, those things were happening in the region, right? Time is this, space is this, three dimension also XYZ direction, right? But why did he unite it suddenly into this time of a thing? A space-time continuum, right? A kind of a lump. Now again, you see now what I talked right at the beginning, that we have to think a little bit abstract. Now you cannot think space and time. It is a lump. It is a kind of a mud clay where everything is united. The first reason was that The if two events are happening simultaneously at one point in space, which is not also simultaneous for another observer in another point of space, right? So the concept of now and then, of here and there, it does not exist, because Newton told that time for me and Rajagopal sir are different. I have a T1, he has a T2, Palomi has got T3, Monica has got T4. So the first thing is that if time is not different, then why will we measure time as different, right? So, and also space is not different, because Newton told that space here is different. No, if the light speed of light is constant absolutely, then I am observing the light coming, like the experiment on the train, which the person sees the light first and then it hits and it hits. That means it is the same light which is coming different only because the speed or the frame of references are different. Then it is an awful foolish thing that why will we make space as different, because space is not different, it is only relative to each other, right? So the constancy of the speed of light tells that space and times must somehow adjust, right? So I have given, imagine a stretching, shrinking this one. If I'm putting it in a rubber sheet, that the distance and time intervals change and it maintains a constant path.
Sir,
Yeah,
excuse me.
yeah,
Sir, can I say something with
sure,
this
sure, sure.
different inertial frame? Sir, there was one thing where that one train was moving and two
Yes,
lightning hit
right.
at two
Yeah,
points
yeah,
A and B,
absolutely.
and
Yeah,
the person in that the person looking from outside the train will see that they happen simultaneously, but the person
simultaneously, but here they
moving
will
in
say,
the
yeah, absolutely. That is the
yeah,
thing.
yes.
That is the thing. So here you see another reason was that because general relativity introduces the concept of space time, although it came later. Now, if everything is getting slowly united, then why will we keep now and then and here and there and time one and time two? Right now, you see the philosophical implication, how everything is getting into one single dimension. I mean, it's a one single structure. Also, this light cone, which is the Minkowski space-time, you see different observer moving at different speed will have different light cones, obviously, right? And this will again blur the lines between what has happened, what is happening, and what will happen. Remember, this Minkowski space-time is for flat space-time. Flat means square, but the metric is 0, 0, 1, 0, 0, and so on. But here we are talking about a curved space-time. So all this and the Michelson-Smalley experiment actually motivated Einstein that why then, if that is simultaneous, if time is not different, then why will we keep for time to be different and space to be different? Because otherwise the calculations will become much problematic, right? So that is, these are the reasons which united space and time together. So observations led Einstein to realize that they are not different, but they are actually woven into one single space-time. Okay, here is a very quick, interesting area that actually Maxwell's equation, which we read today, or maybe Sagar would be reading in a few years from now, were actually a set of 20 original equations. And it was this person, Oliver Heaviside, who actually united all those equations into four equations. But originally it was 20 equations. And I have got a very interesting history, which is called a brief history of Maxwell's equation in my channel. If you want, you can go ahead and look into that. So now the question comes here is that all those equations on the left hand side, which you see, classical equations. Okay, are you getting me? Classical equations. All these classical equations now need to be united using relativity. Why? Because light of speed is constant. Why? Space and time are not different. Why? Because light is defined by electromagnetism. So the first thing that Einstein has to do is that how we can use relativistic equations to make Maxwell's equation relativistic. And this is the first thing which is called unification. The first unification took place by Isaac Newton when he founded gravity, because gravity was thought something different on earth and something different on astronomical scale. So it is called the first unification. When Newton discovered this capital G and that F equals to G m1 m2 by r square, he united cosmology and terrestrial equations into one equation. That is called the first unification. Second unification is this, that relativistically, now we know Maxwell's equation are relativistic. Third will take place when this Maxwell's equation are will be united with quantum mechanics using quantum electrodynamics. So the unification has already started, right? So now you see that I don't want to explain these are tensorial equation which will take again a huge amount of time, but I just wanted to make that this is actually where the equations are united relativistically. Okay, so you see this partial differential equation, these are all tensor equations. F mu nu is our dimensions of space time, we will come to that. Okay, now the question is that what is the advantage? Suddenly, why will Einstein out of the blue will make the equation relativistic? Now here you see something which I would like to tell. If I take the original, yeah, field tensor actually, yeah. If I take the original Lorentz, I mean to say Maxwell's equation in a flat space time, both of them are flat. Okay, we are not moved into curve, both of them are flat. But if I make a Lorentz transformation in the sense that x is boosted to x prime, t is moved to t prime, my question is that will the same equation give result to the same equation? The answer is a big yes. So that means Maxwell's equation had the property that if these equations are used in terms of relativity, it would yield the same result. And what special relativity tells, yes, yeah, ask me a question. Yeah.
Sir, my question was this this Lorentz transformation constant, can this be transformed into a matrix?
Yeah, definitely. Definitely it
Okay,
can be
okay,
transformed into a metric.
okay, okay.
Okay. So So you see the result is the same. So that means it has the property of using the relativistic, and that is why we say that the laws of nature are invariant under all frames of reference. That means electromagnetic equations, if takes place in one frame and another frame are different, that means it is not a relativistic equation, right? It should be same for all frames of reference. So that is one important property. On the other hand, if you try to relativistically transform the Galilean equations, which are also, I mean to say, transformation equations, right? It won't, because it will give something weird result, v plus c, which tells that the speed of the light, something which can move greater than the speed of light, which is not possible. So we define Lorentz transformation as transformation that this line is important, preserves Maxwell's equations. This one is important, I make it bold now and little bit bigger also. It preserves Maxwell's equations, that means that the result has to be the same. Okay, but Maxwell's equations are not invariant under Galilean transformation. If you do a little bit of calculation, you will see it gives a result which is greater than the speed of light, and it is not possible. Now, you see, this thing is actually the basic idea. Yeah, physics must be same. Yeah. Now, this is actually the basic idea of tensor. We have already started moving into tensors. That means we need a kind of a mathematical tool. Are you getting my point? So that whatever changes happen, you bend, you turn, and you twist, you run, you move, whatever it happens, the laws of the equation or the law of inertial frame or the laws will be the same. And this is not only true to physics, it is true to differential geometry. And I recently made a very long 1 hour video using clay models of my daughter, which is called topology. Topology also tells the same thing, that if I got a kind of a box or something, if I bend it, I twist it, I turn it, the same property of the box will be the same, though I can do anything that you want. So this is the concept of invariance, which is in physics, which might be even in chemistry, I don't know, but it is there in pure mathematics and topology also. Okay, so from here, what we see is this is the summary, that general relativity is more than mathematics. I mean to say more than geometry. The bending of light is shows that the space time is curved, and in order to measure the laws of invariant, these has to be what is the difference between topology and differential geometry? Well, Karan, it's a huge amount of difference. I will send you a video which I've talked. Differential geometry is something very local, and that is why we will use differential geometry in today's webinar. But topology is something on a very global scale. So there's a huge amount of difference. And also the mathematics is something, there's a lot of difference. I will tell you what is the difference. I made a video also on topology and differential geometry, right? Okay, so 1 hour, are you all enjoying? Okay, 4 or 5 people have gone
Yes.
out. I understand that
Yes.
it's not okay
Yes,
this.
yes, yes.
Fine. Okay, fine. So yeah, Ayushi, tell me your question. Yeah, Ayushi, your question. You have a question? Okay. I've got to cover a lot of other things also. Okay. So from flat space time, we are moving into curved space time. Okay. So what is the postulate? Again, we look into what are the postulates of general relativity. It tells that again, it is almost same like special relativity, right? You're enjoying, right? So tensors are invariant. Absolutely. I will come to that. I will come to this tensor part. So the laws of physics are the same like special relativity, and the gravitational acceleration is the same for all observers. This is the basic, I mean to say, the postulate of general relativity. Yeah, thank you, Rajagopal sir. Okay, now here you see a kind of a basic idea. I will quickly go over because there are a lot of things to cover. In a kind of a flat space, this vector you measure, it is the a vector, right? On the left hand side, you see I twisted this to a curved space time. Can you repeat last slide? Okay, so the last slide was this one. The laws of physics should be the same for all observer, and the gravitational acceleration is the same for all observers in gravitational field. I want to say, madam, prepare 40 cup of tea for my class fellows. Okay, fine. So now you see what is happening when I'm moving from flat to a curved space, right? What is happening? The vector is the same, a, right? But the components of the vector changes. See, a prime x is a little bit longer, and a prime y is also a little bit longer, right? You everyone got it? So this is the thing. Now here you see I rotate it. So what I'm doing, I'm trying to change. So from this, when I rotate the frame of reference, again you see a prime x is a little bit bigger, but a prime y is a little bit shorter. Yeah, the components are not invariant. Yeah, under the transformation. I'm to say no, the components are invariant, but the vector remains invariant. The components a prime x, a prime y, these changes, but the main vector will remain the same. So now you see that from flat space we are moving into curved space. That means the mathematics of flat space won't work out. So all those left hand side equations which you can see, these are very good. I mean to say vectors, etc. These are all okay to measure something on a flat space time, but it is not good in terms of a curved space time. Now this is the question: what is this surface called on which this all those curved space or curved mathematics takes place? We are now first going to understand the first mathematical component of general theory of relativity. What is this surface called? And it is called as manifold. And now what we are doing is that we are going into differential geometry a little bit, and then we will come to the Einstein field equations and complete our webinar. Now, what is the meaning of manifold? Simple, many folds, right? So any surface which has got lot of folds are actually called manifold. So on the left hand side, you can see it is called a manifold has a small area which looks like Euclidean, and manifold is a topological space that is, anyway, we can leave the right hand side part. Okay, so what I'm trying to tell over you is that, say for example, this is a place, right? And I draw a straight line, okay, or draw anything like this, okay. Now if you are watching it very closely here, very closely, you will see that the straight line comprises of one, two, three, four, many points, right? This line. But when I move out, when I zoom out, you might say that this is not a straight line, but this is a curved line. Are you all getting me? What I'm trying to tell is that a manifold is something which locally, that means if you zoom in locally, it will look like a Euclidean space. I mean to say normal Euclidean mathematics, Cartesian mathematics. But if you zoom out, yes, like our Earth. But if you zoom out, it might be curved, twisted, turned, whatever. That is what is called a manifold, right? So here you see that if I see out, it is global, okay? But if I zoom in, it is local. That means now you will understand yourself why we are using something which is local. why we are not using global. Karan just asked me, can spherical coordinate equations applicable to manifold? Absolutely, absolutely. Sphere is a manifold, Muhammad. I mean to say, we in differential geometry we deal with spheres, right? So now the question is that you might ask that why are we doing it something locally? Why not globally? Karan asked me the question, why, what is the difference between geometry and topology? So the answer is that global mathematics is very difficult, local mathematics is easy. Same like local people competition is less, global competition is much more. And this local mathematics is nothing more than calculus. It is nothing more than calculus. So here you see, if I get these type of surfaces, so straight line Mukim, yeah, because we know the mathematics of local, absolutely. So this has got a positive curvature, this has got a zero curvature, and this has got a negative curvature. But if I use the dy by dx calculus, then I can use the rules of calculus and I can quickly calculate what is the structure of that space. And now do you understand why we are using calculus? Because we have to deal with curvatures. Here, Euclidean Pythagoras' theorem is not going to work out. So here it you see, if I zoom in and zoom in and zoom in and zoom in, I get a local structure, which is the straight line. But if I zoom out, zoom out, zoom out, I become global. So Karan, now you can understand this one, that why topology uses set theory and why differential geometry uses calculus.
Sir, excuse me. Sir,
Yeah,
can I say something?
yeah, sure.
Sir, one mathematician, Carl Friedrich Gauss, once tried to measure
Yes.
the curvature of the Earth. He tried to measure the angles of the triangle, and they turned out to be more than
More
180
than
degree.
180
They
degrees.
turned out to
Absolutely.
be 180 degree. So,
Yeah.
because it was local, the
Local. Right,
plane was
right,
flat.
right. Absolutely, absolutely. So here is a nice video of mine that how differential geometry contributes to general relativity. You can later have a look. I will pass on to that. That this term manifold was actually coined by another person whose wallpaper is there in my personal mobile. Don't laugh on me. I'm that kind of a person. So it was Bernhard Riemann, and I call him the grandfather of mathematics. I think he died at the age of 42 and 43, and he was a very poor person. His father actually went bankrupt to send him at Göttingen University, and under the Carl Gauss, you were telling Sagar, Carl Gauss, now you see he is there. So he actually gave a very boring thesis paper, which is called The Foundations of Geometry. And it came out to be one of the greatest book which is still being taught in universities. It is called On the Hypothesis which Lie at the Basis of Geometry. The date was June 10th, 1854. And Riemann's problem, yes, absolutely, it is still unsolved. And this is the book where he first laid the foundation of manifold. Now, you see, one thing now it becomes very clear that Einstein was not aware anything about differential geometry. I will show you nothing about tensors. And it was done way back, I mean to say, much, much earlier to 1915. And it was Bernhard Riemann. So you see, now we come to the concept quickly that what are tensors. So it comes from the Latin word tender, that means stretch. So you get the tender muscles, like we say the tensorial muscles. So you're on the left hand side, you see there is a sphere. Mohammed was asking me, Mohammed, now you see this is a sphere and it has got some amount of information. Now, if I stretch that, now the question is that why I am stretching? Why I am stretching? Because obviously it is a curved surface, it will stretch. So when I am stretching that, so that red information also gets stretched out, obviously. So if the information is over here, say for example, right, and if I stretch it, the information will get stretched. Question is that how I am going to measure that stretched information? Yes, remember that the vector cannot change, the components can change. So, what is that equation? Now, maybe you are thinking that why don't we use vectors? No, vectors cannot do that. There is a reason, I will show you. So originally, as you see, yeah, by transformation, originally, as you see, the tensors were actually invented by the use of crystal structures. When mathematicians were starting to study crystals, they were invented tensors because structure crystals have many directions, this, that, etc. And also, I would like to show you that you see here that a person is throwing a ball, okay, in one frame of reference. The same ball is being thrown when it is rotated and when it is extended. So the question is that how can I measure the throwing of the ball if the frames are changed? And that is why Einstein told that general laws of nature must be expressed in terms of, I would say, by identical equations, whatever may happen or whatever the way we are moving. So one was special relativity, when from one frame of reference we moved to another and where we united space and time into another. We also united Maxwell's equations using relativistic. Now we getting to the next challenge, that how the frames are moving, and they are not, as Rajagopal sir has told, that it was not inertial, now it is non-inertial. That means non-linear. How we can do that? Here is again a video which you can look later. Tensors, a beginner's guide, which you can do how it shapes relativity. So what we understood from here is that tensors are objects that can take care of magnitude, direction, and plane. Remember, vectors have got magnitude and direction, but it cannot say on which surface of the crystal it is taking place. That was not defined in vectors. But in tensors, we can do that. We can say that x and y is taking place. Yeah, vectors are better, but we cannot use that. X and y is taking place, and this x and y is happening on the z axis or on the z plane, on the other part of that. So if I heat a crystal, which I have not shown in here, in case of a glass, it would expand uniformly. Chemistry people like Prashant can tell me. But if you heat a crystal, it would expand in different directions. So if it expands in different direction, it becomes very difficult to measure those magnitudes. So that is why we need tensors. This is also another video which talks about manifold. You can later have a look onto that. Now, here is a very interesting history. So, I'm a physics person. Oh, you are from physics. I'm so sorry. Then you see that Einstein was not aware about that. I actually talked about this person in one of my live classes, Marcel Grossman, very important, who made a contribution to history. Tensors only specifically plans like plane or curve. It can takes place in both the places, plane as well as curve, right? And here you can see I have underlined few lines, that this is basically called the Grossman. This is actually taken from an archive. This is the original handwriting of Marcel Grossman, and it shows that he actually used this tensor. And then you can see that, I'm so sorry, yeah, so this I have written. So it was actually Marcel Grossman who introduced the concept of tensors. He educated, I have got there's a book which is called Subtle is the Lord. I will put it in the chat box. If you can please purchase it, it will be great. Subtle is the Lord. Abraham Pace. Abraham Abraham Pace. Okay.
It's a
This
very
is a
famous book,
very,
Abraham Pairs, yes.
yes, it is a very precious book which actually speaks how Einstein was confused and he was frantically searching because he don't know about tensors, and it was Grossman who actually introduced the concept of tensor, and he finally found what we are coming, the central and the last part of our webinar, Einstein field equation. How are you all enjoying? Can you just unmute and talk to me?
Good, sir. Very nice.
Good, yes, I shall do.
We are fine, sir. We are listening to you. We
Yes,
really
sir,
enjoy.
enjoying. We are.
Okay, I know it
Great,
is a
sir.
very,
Yes, sir. It's a
Enjoying.
great lecture.
yeah, it is a very hectic one, but hold on, I will be able to explain you everything. Okay, most interesting part, Einstein field equation. What is the left hand side telling? Okay, Amal, you are still there. Okay, great. Okay, so the left hand side of the equation tells that the geometry of space time, that means how much matter is causing the curvature. I mean to say, the tools that we use to measure curvature. Formula general, yeah, absolutely, absolutely, absolutely. On the right hand side, this equation tells that how matter movement creates the curvature. So if left hand side speaks of the curvature and the right hand side speaks what is responsible for curvature, and if we unite both of them, then we get the equation. So that is what I have written at the bottom. Space time tells matter how to move, and matter tells space time how to curve. It's very important, right? My 9-year-old niece is also watching with me. Okay, great, great, Praveen. Thank you very much. Everybody should be encouraged. Yeah. Okay, now I will try to explain the components of Einstein field equation, which is the final part of our webinar. First of all, I will like to tell you that this now from here I will like to make a kind of a not a warning but a note, but because these concepts are highly complex. Okay, I won't be able to give you a very good idea about all of those in such short period of time, but I'm going to give you a fairly intuitive mathematical idea so that your further studies you can take it up from here, because each equations will require 1.5 hours time to explain. I'm so sorry, which I cannot do that, right? So that it is. Okay, so here you see that there are certain constants. One is lambda, which is called the cosmological constant, and there's a book in my shelf which is called Brilliant Blunders, and this was the first blunder which Einstein made. He thought that the universe is not expanding, it is constant. Okay, the second is 8 pi. How the 8 pi is coming from Poisson's equation and the sphere, I'm not talking of that. G is the gravitational constant and C is the speed of light. Why it is 4? Because of the dimensional analysis. We will look into that much later. Okay, the first R on the left hand side is called the Ricci curvature tensor. I will explain that easily. Okay, just first let us understand what is the basic name. We have got a mu nu, which is the dimension of space time. I will explain that also. Forget about the half part. Again, there is a r, which is called the Ricci scalar. Then we have got another g, which is the metric tensor, very important. Then we have something which is hidden because it is contracted, it is not shown here. It is called Riemann curvature tensor. And then you see the t on the right hand side, which is called the stress energy momentum tensor. Now, the curvature tensor, the Ricci scalar, the metric tensor, and the Riemann curvature tensor, all of this measures the curvature in different ways. In different ways, okay. And the only component that measures that if matter is present, how will I define that matter, the stress, the energy, the momentum, everything that is on the used by T. So first star is the Ricci, next star is the Ricci scalar, then comes G, the metric tensor, then again comes the G, which is a metric tensor, then comes the T, which is the stress energy momentum tensor. Okay, now you see what I am trying to tell you, that each of these mu nu are 4 dimensions of space time. Remember, Einstein already united space and time. So length, breadth, height, and time. 4 plus 4 plus 4 plus 4. How many it comes? 16 total equations. That means what you are looking at is basically a 16 equations. I would say 16 partial nonlinear differential equation which is written in one form. But it is not one equation. That is why we call it Einstein's field equations. It is a plural, not a singular. Now, out of those 16 equations, 6 of them are very common. I cannot show you because again I have to use that matrix. 6 of them are common. So we cancel those 6. And at the end, absolutely Manan is right. We get 10 equations which you need to study. Here you see, so G0110, G3223, in this way, all those things gets cancelled out, right? It is a matrix, simple linear algebra, and we get only those 10 set of equations. Now you see what actually metric tensor does. You can think in this way. In Cartesian coordinate, when we try to measure the angles, the distance, etc., here we don't have any angle. Here we don't have any distance, it is all curvature. But I'm trying to give you an analogy that all these things are actually measured by metric tensor. That means how much is the spread, how much is the angle, how much is the distance, all those things are measured by metric tensor. So here you see, this is a nice thing that the G, I mean to say, here the G is the gravitational acceleration, not the metric tensor. That means the more the massive the object is, the more is the G. Are you getting my point? So you see, G for Jupiter is the highest. G for Earth is less. and G for Mercury is even less. Why? Because you see the size, that is the weight in terms of kilogram, varies. Now, this is what Einstein's field equations measure. It's a practical demonstration. That means if I want to measure the curvature of Jupiter, right, I will look into what is the value of G. Oh, 24.79. That means the gravitational acceleration and the gravity is huge. Yes, why gravity is huge? Because the curvature is huge. And this curvature only causes the gravity. We will look into it now. But if you talk of Mercury, it is only 3.7. That means the gravitational acceleration, the G, is less. Why? Because the curvature is less. That means from now, from today on, we won't speak that it is a gravity. Yeah, yeah,
Sir,
sir.
shall I ask one? It's
Yeah,
just a
sure.
fundamental doubt. I understood the idea you told Jupiter has got more curvature compared to Mercury,
Right,
but Jupiter is a huge radius. It has got a much more bigger dimension, much more
right,
larger.
right.
So when you say larger radius, by the normal geometry that I know, the curvature is lesser, no? And one by r is the curvature.
1 by r is the curvature. Yeah. But yeah,
So
I will come to that. Actually, what you are taking is the curvature. Now, here we have to talk whether it is an intrinsic curvature or an extrinsic
okay,
curvature. That we have to take into account.
fine, fine.
Right. So here we are taking out the outside, the extrinsic curvature, but 1 by r again would be the intrinsic. That is the, we have to take the volume part also. So that I will explain it. Yeah. So this is what it does. Now let us see in a very easy language what is this metric tensor. I call it as a space-time ruler. Okay, so you can read it out that the metric tensor is the measurement of the blanket. Imagine it's a huge blanket, and you're telling how much it is stretched, how much it is squashed, each point, right? So these things of a blanket which is being stressed, etc., this is actually measured by metric tensor. And a massive star sitting on a blanket obviously would, create a much more heavy grid, and that is why the g mu nu will be much higher, and the less one will have a less mu nu. So it is a space-time ruler which actually checks about the curvature. Now, what is the Ricci curvature? It measures the wrinkles. Okay, so if you take a blanket, okay, try to imagine a blanket, it will have wrinkles, right? Now, if you imagine the arrows which are actually measuring the grid, try to understand this one. I think this is, yeah. Here you see these arrows. So if I get a bigger grid, what Rajagopal sir was telling, huge curvature, then the arrows will be pointing more sharply inside. If you take a less curvature, the arrows will be less. Okay, is it all clear, or shall I use my Jamboard ones to explain you a little bit more? I think that will be a little bit better. Just give me a sec. I
Yes,
think
yes.
that will be easier for all of you to understand, because if you're all
Yes,
here,
sir.
then why don't we use the best of our time? Yeah. So I will just, okay, just a second. The Jamboard is coming, coming, coming. Yeah, now you can see the Jamboard, right? Yeah. Okay, so if I take this kind of a thing, which has got a very high kind of a curvature, something like this one. So what is going to happen is that, and this is in a kind of a grid, right? So this is a grid. I'm going to say these are all grid lines. Okay, so if I'm trying to measure a kind of a curvature over here, so the arrow will be much sharper over here, this one will be much sharper. But compared to that, if I take a less curved area, and these are also grids, say for example, even trying to measure, the arrows will be less pointing towards. So what happens is that this G mu nu will actually be measuring. So from here to here, what is the stretch? What is the arrow? And from here, if I want to move here, how much the stretch will be going? So all these things will be actually measured by G mu nu. Are you all clear? I mean to say, it is difficult to explain, but I hope that you can get this point. Okay, so now I will go back to the this part. So I have to, yeah, quickly rush because, yeah. So now I go to my screen. Just a second. Yeah. It's just coming. Right. So this is actually the kind of a measurement. I mean, so that is why I told you it is a little bit difficult. So the wrinkles, that means how much space-time is curved in directions. I will just show you an example. Now you see this one. Let me zoom a little bit more so that it is clear. Now you see that two initial geodesics which actually started, I mean, it's a two straight lines. It should be actually parallel, but they actually diverge, right? So what the Ricci tensor actually tells is that how much the space-time volume, the amount of volume which is between these two geodesics changes in each direction. So that means you understand, if it is a positive curvature and if it is big, the volume change will be higher. If it is negative, it is spreading out here, then it will be lesser. Now, this volume change, just for a very technical understanding, this is not the ordinary volume, it is the differential volume. We need to understand because it is all taking place on a manifold, which is very differential in nature. So, it is not that the volume pi or any Euclidean volume we cannot calculate. We have to use the calculus because it is a very infinitely small change of volume which happens. Right. Next, we come to this one, which is called the Ricci scalar. Ricci scalar, we call it sum of wrinkles. Parallels cannot, yeah, and intersect in Euclidean. So here it tells that the grand total of all the wrinkles. This one told what? This one told that it measures the wrinkles. That means in which direction the wrinkles are happening. Yeah, like longitudes. And here we sum up all the wrinkles, right? R, mu, nu, etc. And the higher value indicates there are more wrinkle, lesser value indicates less wrinkle. And Riemann curvature tensor is actually which is called how this curvature twists and shears in different direction. I'm very sorry, a Riemann curvature tensor is something which I won't be able to explain too much because I have to show the derivation and I don't have the time. So it is basically another kind of a tensor which actually takes care of all the bends and turns, right? And it is looks like this. It has got an upper indices and it's a four dimension, you can see r with a row on the upstairs and the three indices at the lower. So that is, it is called four dimensional curvature tensor. And stress tensor is very easy. That means how much energy is present. That means if it is an elephant, it will cause a more curvature. If it is me, it will cause a less curvature. That means it measures that the matter of energy, etc., which is present. Okay, I will quickly show you what is Ricci curvature tensor geometrically. Now, this is actually discovered by Gregorio Ricci Curbastro, and Tullio Levi-Civita was actually his student, and this is the book. Okay, now you see this. This I have already shown. Now here you see the ball is shrinking. That is called a positive curvature. And if I take a ball, again the volume is the differential volume. It shrinks. It shrinks. Why? Because it has got a positive curvature. Now, this is actually, this volume change is being denoted by Ricci curvature. It is all about curvature. Here you see a better thing. Here the Ricci curvature is 0. Why? Because it is flat. Here Ricci curvature is greater than 0. Why? Because it is shrinking. Here the Ricci curvature is less than 0 because it is expanding. That means the curvature, which is technically called the geodesics, and the volume change, how the matter will move along that kind of a geodesic, that is being understood or measured by Ricci curvature. That means it is measuring what? It is measuring the curvature only. Okay, what is the metric tensor? Let me quickly explain. It is just a metric. Okay, now here is a common misconception. People think metric tensor means general relativity. No, metric can be anything. Milliliter is also metric. Kilogram is also metric. Okay, metric tensor in terms of general relativity means that, say for example, we are measuring Indian rupee, then Japanese yen and Thai baht. And here also we are trying to measure the distance from my home to my college. This is a measurement straight. This is called Euclidean metric. And if I take curved space, I call it a taximetric. So that means it is a type of a measurement in one way. Now here you see, if I take a differential, I would say differential Pythagorean, you understood that, right, sir? So if it stretches, okay, the x stretches, I make it 2 dx square. If both x and y changes, I make it 2 dx and 2 dy. I'm going to say using Pythagoras' theorem in terms of infinitesimal calculus, right? Now here you see what happens. This is the concept of metric tensor. I have taken an unstretched information. That means a kind of a piece of cloth. Okay, this is the piece of cloth which is not stretched. Okay, now I am mapping that and putting on an stretched information, that is the sphere. So if I know that unstretched Euclidean metric is 0, say for example, or G11, G22, whatever, if I patch it over a sphere, then the information gets stretched. Now, in order to gather that stretched information, I do the tensors. I do the mathematics of tensor. But before that, remember, we have stored the unstretched information in the Euclidean metric. That is this one, G11, G12, G122, and so on. So that means if I can know the general metric of a Euclidean space, and if I map it over a sphere, then I can use the unstretched information to get the stretched information. So the metric tensor can be different from, yeah, absolutely, Manan. Metric tensor is different, Schwarzschild metric, black hole metric, all those metrics are different. There are many metrics. And that is why somebody asked me that exact solution. We take Schwarzschild black hole or Schwarzschild solution as the easiest solution. That means there is no charge, black hole is not moving, there is spherical symmetry. Because if we try to take all the different things, if we take a charge, if we take a movement and all those things, what is going to happen is that my equations are also going to become very complicated. So that is why we take exact solution. That means a basic minimum, a kind of a very uncomplicated model. And then there is curve solution. Yes, curve solution. So all these metrics are different. So what is,
Sir,
yeah,
sir, can you go back to the slide where there was a formula like dA square equal to
yeah.
yes, this one. Can you explain? No, no, not this one, the next one.
No, this
Yeah,
one
can you
I will
explain?
no. This will take some time because I have to first explain what is G11, and this is basically a quadratic equation which actually takes into account the first component of the metric tensor G11. You come to me later,
Okay, okay,
Sagar. I will explain you. This will require a mathematical derivation, which I cannot show you
okay.
right at this moment. Okay, okay. So Riemann curvature tensor, I'm quickly, skipping. This is what the Riemann curvature tensor looks in terms of Christoffel symbols. So Riemann curvature tensor is something, yeah, distance between two moving points. It is something to what we say, we compare the vectors. So if I want to measure, so here is something, let me make you understand. If I see on the left hand side which one is bigger and which one is smaller, we can understand by comparing two vectors, right? But it is not always true for a spherical or a curvature. So say for example, if I take this black vector, okay, and if I move keeping it parallelly, and if I come back to the red point on the triangle, and if this vector overlaps this vector, that means what? There is no curvature, right? If I move and I come back and it overlaps, that means there is no curvature. As here you can see, it is a triangle, it is flat, it has got no curvature. Now see this figure very, very closely. I started at V, where the black man is standing, right? I'm trying to parallelly transport, but the entire purple vector is moving Y because of the curvature. And when I come back, the blue one, you see the V prime one has changed. So this is what Riemann curvature tensor does. So the metric would be 2 by 2 for x and y, 4 by 4, yeah, and so on, right? Yeah, yeah. And could we also calculate distance between 2 points of the manifold to time difference? Yes, metric tensor all does this magic. You're right, Manan. Absolutely. So you see that if the vector is being coming back and it is showing a difference, that means there is a curvature. Okay, and this difference between the blue vector and the yellow vector is actually what Riemann curvature tensor measures. Now, due to lack of time, I have actually skipped one important thing which is called Noether's theorem. Maybe Rajagopal sir or maybe all of you know. Now, Noether's theorem was actually a problem which Einstein and everybody faced, and it was the problem with this law of conservation of energy. Yes, Noether's theorem. Noether's theorem was a time when at Göttingen there's a famous kind of a story. Just give me 2 minutes time. It tells that when Einstein, David Hilbert, and Felix Klein, all of them were finding that general theory of relativity is actually violating the law of conservation of energy. I won't go right now because it is very mathematical and complicated. And they called Emmy Noether a lady who never got any position in mathematics. She is, I mean to say, she's a one of the most brilliant mathematician ever born. I can tell, don't take me wrong, she is even better than Einstein. If you talk to me, if you take my opinion. And Emmy Noether actually framed two theorems, Noether's first theorem and second theorem. And using this parallel transport, Emmy Noether actually showed that what happens in a flat space time, you can actually calculate all the energy over here. How to integrate? Right? You integrate this point, this point, this point, this point, and you go to the total energy of this particular place. But it doesn't happen in a curved space. In a curved space, when you're moving, you see this diagram, and when I'm coming back, the two vectors are different. So if the vectors are different, then how I can quantize and measure the points of energy and momentum, etc. So that was a big problem. Einstein cannot solve it. David Hilbert cannot solve it. Felix Klein cannot solve it. And Emmy Noether solved it. And he told that the law of conservation of energy locally is being conserved. And how we have done that is another episode, but I don't want to really go. But this is something, I mean to say, phenomenal achievement of Emmy Noether. I have already made a small video on a book of Emmy Noether. You can later look into this, so that would be great. It's very helpful if you create a playlist on this topic with mathematical derivations. Yeah, I will definitely. I've done already some of them. Okay. So from here we come to the next one, which is the stress energy momentum tensor. And here you can see what it is if you ask me. So it is a house. Okay, it is a house where everything related to matter, momentum, energy, stress, flux, shear stress, everything is located over here. But remember, it is a tensorial object. Why? Because it is curved. Because we need different spaces. Because the vectors should be invariant. All of you there with me? Are you getting my point?
Yes, sir.
So here you see, if I take the
Yes.
matrix of stress energy, right, you will see that it measures energy. Energy is responsible for curvature. Pressure is also responsible for curvature. Movement of and matter from causes energy to transport from one to another, and it causes the curvature. So all those things, momentum, density, pressure. So Rajagopal sir, you being an engineer, I think you will
Yeah.
agree to this, right? So all those things actually causes the, I would say, the stress which causes the curvature. So left hand side we have seen Ricci, Riemann, metric, all those which measures the curvature. Now we are, what we are finding is the right hand side, which is telling that, okay, so if I and an elephant is different, then elephant has also got energy density. What is the meaning of flux? Okay. Sir, I give it to you. Elish is asking what is the meaning of flux. Sir, if you can quickly explain to him, I think you're the right person. To Raja Gopal sir.
Flux in general is something that flows across a given area. It could be energy, it could be electromagnetic lines of forces, or anything, or even you can think of a fluid flowing in a pipe across an area is also a flux. I suppose that's what I can explain.
Absolutely. You can think, Elish, in this way: the ray of sunlight streaming across your window. That is called the flux. Flux has got many calculations, etc. Why is T001 energy density and not pressure? Yeah, very good question. Energy density and not a pressure, because it is
Is
right
it
at
correct,
the,
sir?
yeah,
Flux is directly proportional number of field lines passing through a given area.
absolutely. This is a technical one. This is energy density because this actually corresponds to E equals to mc square, and c being the speed of light will always take the highest position in the matrix. I can explain it later a little bit why this is energy density. Energy density because c being the speed of light and the highest that will have the top place in the matrix. So that is why it is called. Okay, so all these actually measures the momentum. I mean to say the stress energy tensor. Now we come to the final thing, which is called this line. This is the if you ask a rickshaw puller, this is a famous. If you remember Amal Kumar Chaudhary, one of the greatest Indian theoretical physicists, he gave an interview and he told that geodesic. Sir, can you explain geodesic? So he told that if you ask a mathematician that where will the tram go, he will see that you give me the initial position, etc., and the second derivative, and I will do the calculation. But if you ask a rickshaw puller that well with the tram will go, the rickshaw puller will tell that it will just follow the straight path or the path which is on the tram line. That is the concept of geodesic. The geodesic actually tells that it generalizes again the straight line, that which is the shortest distance. The shortest distance, and this shortest distance, remember, it is something which is equal to Lagrangian. That is, nature is very lazy, right? That is the same thing which is coming. I'll come to that quickly. That this is called the so the matter is causing the energy and pressure. This pressure is causing the curvature, and this curvature is being measured by the Riemann, Ricci, all those things. And this curvature is basically a manifestation of what we called is that is gravity. Okay, all clear? Okay, I will just quickly go for a whirlwind tour, maybe not for Sagar or others, that Newton's laws of motion, if I take it, all those things, I mean to say, if I take the second derivative of position, I get velocity equals to dx by dt. From here, I can use the chain rule of calculus, and what I can get is that acceleration. It shows that this second derivative of the position function with respect to time acceleration equal to d square x by dt square. Now, if I take the concept of geodesic, it tells that uh, not the same as the shortest curves between point, but though the two concepts are close to each other, it generalizes the notion of a straight line, right? Now, this is what the ball will roll in a straight line, and here the ball will roll down the hill. So, what I am trying to make a point is that the curvature of space time is causes the particles to accelerate. This is very important. So, the curvature is causing the particles to accelerate, and the absence of any external forces, the only force acting on it is the gravitational force caused by the curvature of space time. If another external force is not present, then what is causing the ball to move? It is causing the gravity, which is the curvature. Now, here you see quickly, this is actually the geodesic equation. I think Rajagopala sir or others will appreciate this. Now, you see this d square x mu followed by ds square is the same, which is d square x alpha and d this one d t square. This is what is called the tau. Okay, I mean to say both the equation sometime is written as tau or etc. ds is also written as d tau. Again, ds is written as d tau. Now see what happens here. So here d square x mu, which is the dimension, this term represents the second derivative of the coordinate x mu with respect to the time. Remember that in Newton's second law of motion, we also took the second derivative, right, sir? You see here is a equal to d square x dt square. The same thing happens over here. Isn't it beautiful? Right.
Sir,
Here, yeah.
sir, excuse me, I have a question. Sir, while solving for the shortest distance between 2 points, we take the Lagrangian and plug it into the Euler-Lagrange equation, and
Equation.
then we get a linear function.
Right.
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 So now if we do it in a curved place, so will the function also give a curved function like that, or still then it will be
No,
straight?
no, no. In case of a geodesic, it will result into zero. I will come to that.
Okay,
It
okay,
won't give you a function. I will just come to that. Okay.
okay,
So
okay.
here you see, I have written in terms of Christoffel symbol of the second kind, which is basically there are three kinds of Christoffel symbol. I'm just quickly skipping the first kind, which is defined in metric tensor. The second time in terms of covariant derivative, and the second kind, which is in terms of covariant derivative. So I'm just skipping this part. Now here you see this one is very interesting. This gamma mu followed by alpha beta, these are related to the curvature which involve derivative of the metric tensor. Now mu is the index, right, in which the covariant derivative is taken, and alpha beta are the coordinates, right? So it actually is that Christoffel symbols in the lower indices, it means that they possess a symmetric property. There are many I would say features of things being a symmetric. The finally what we see from here also dx alpha equals to 0. So here also x alpha denotes respect to proper time, same with Newtonian equation, right? And now you see this one, you see this d square x mu divided by ds square. Now this x alpha is the first derivative of the coordinate with respect to time, and here also dx is the first derivative of the position with respect to time. Right, sir? You see the similarity between second Newton's second law and geodesic equation. This d square x, this shows that the second derivative of the position function with respect to time, here it is dt square, and here also it shows this ds square and dt square, both of them are similar. Here also the term represents the second derivative of the coordinate with respect to time. Here also it is representing time, here also it is representing time. But only thing is that we are plugging in some more things like alpha and the gamma terms because we want to represent in the Christoffel symbol. So what it actually shows is this: theory of gravity, Newton's second law of motion is applicable to Newtonian gravity, non-relativistic solutions, and geodesic is more generalized, both non-relativist. So the basic idea of showing this derivation is that the second law of motion of Isaac Newton is something which is similar to geodesics. Only the difference is that because it is in a flat space time, it is in a curved space time. So we have to consider a lot of symbols, etc. The last part is that you see that gravity is bending the space time matter. So if the sun is present, which is a huge mass, so it causes a huge curvature. So instead of the straight line, the line will now follow what is called the geodesic. This is important. So somebody asked me at the beginning that photons, do they have mass? No, photons are traveling in their own path, but it is the geodesic curvature that the photon has to do like that, and that was actually done by Arthur Eddington. So here is a very nice video. Does gravity affects the path of light? You can look into that. And finally, we come to the last part, which is the black holes, which somebody might be interested. So we know that how space-time is curved with the left-hand side. We know how the right-hand side causes the curvature. And in black holes, you see that it has got an extreme curvature. And here I have not shown, but you will see that the entire equation blows to infinity. I mean to say, not infinity, it will be undecidable. So Rajagopal sir can say that there is a huge difference between infinity and undecidable. So
Singularity is the
yeah,
word.
absolutely. Singularity, right. So when we say that the equation fails, or when we say that the laws of physics fails, this is nothing romantic. It is very mathematical in nature, that the entire laws of physics actually falls down. It blows up to something else. So that was actually by Carl Schwarzschild, which who first actually formulated singularity was predicted by yeah, it was first predicted by Carl Schwarzschild. And remember, there's a famous story which I don't want to take time, that he was actually lying under the bunker, and I made a just hold on for a second. I will just give it to you. A very this got a lot of views, etc. So I was pretty happy. This actually came up from my new channel. I'm just giving you this shots to you all so that you can look into this. This is the link where I have talked about Karl Schwarzschild and remaining under the bunker of First World War. He has actually calculated the first day. Okay, yeah, Karan has watched that. You can watch this one also. Why this? No, I mean to say, Muhammad, they really do not fail, but the equations actually do not give any solution, and it gives something undecided. So that is why it happens. So remember that Schwarzschild, this one is basically nothing but that anything can be turned into black hole. You, me, Rajagopal sir, this entire universe, provided that it goes beyond the Schwarzschild radius, that is RS. right? Yes, beyond our scope. So here you see all objects can be turned into a black hole if it goes below the Schwarzschild critical radius. And here you see another description where it shows that if the length is more, you just need to shrink Earth to a tennis ball. Yeah, absolutely. I say the black hole is like a hole in a blanket of space. And no, Prashant, we cannot tell black hole is actually a hole. It is a curvature. There is no concept of a hole which is being put up. That is a very big misconception. It is just a extreme curvature. Now you see here, if I take time as a coordinate and it makes a huge curvature, so what happens when we approach near a black hole or something? We say, you see, you know that famous, maybe Sagar has been knowing, a person falling into a black hole, the person outside a spaceship will never see falling into the black hole.
Sir, he will just see him as freezing near the event horizon of
Within
the
the
black hole.
event horizon. Why it is that? Is it yeah, it is a celestial body like sun. Yeah. So why it is? Because time will be so long, the curvature is such infinity that he will continue to see going on and on and on and on and on, and he will never he will see anything like that. Does Newtonian gravity predict any kind of black hole? No, because the concept of curvature was not there. What is the singularities of a black hole? That is another topic which actually tells that all the laws of physics actually fails near that. So here you see, I try to give you a nice idea that if I start with a on the right hand side, the Earth's curvature is less. So if I start at 9 a.m., I can reach on the other end at 11 a.m. But if I take a black hole, if I start at 9 a.m., maybe I will travel more because it will take at 3 p.m. Right. So this is just because of this curvature. And here you see that a person near a black hole obviously will age slower because the entire gene of the body will be slow because of this huge curvature. So when we talk about time dilation and slowing down, we are really talking about all the physical process because the time will obviously be more. And here you see, this is what is called the gravitational redshift. That means from the black hole, which is more, things will be longer, and longer. But that does not mean that we are losing out any energy. It is again conserved using Noether's theorem. So the strong gravitational field pulls the photon and causing loss of energy. Okay, but the loss of energy results in a longer wavelength, which is redshift. There is another opposite of redshift, which is called a blue shift, right? Okay, so from here we move to the final part, which is this one. I mean to say, this is actually called as the research which was being done. And as you can see, I will just show to you that so the and Reinhard Genzel and Geodesic actually first using the gravitational redshift calculated that yes, there is a black hole. And how he did it, this is the most important thing you see here, that okay, this, pay attention to this figure. You see here what is happening. The star S2, you see the yellow one, right? When it is far off from the supermassive black hole, it was looking white in color. You see this? It is white in color. But as it is moving closer and closer and closer, okay, it is turning to be reddish. This is the red shift. And it happened when the star will be closest orbit, that is May 19th, 2018. But you see on the left hand side, extreme on the presentation, the distance is far, so it is white. So that is why, because of this, the distance is wide. So it came closer and closer and closer, and that is why the redshift happened. And because of this redshift and Roger Penrose's calculation, we finally framed that yes, there is a supermassive black hole at the center of the galaxy. So that brings to our end of today's webinar. Thank you very much for all of you. There is a small thing which I would request to be there just for 1 minute or so. Uh, Okay, first I would like to quickly hear from all of you. How did you really enjoy the webinar, or was it too boring or something like that? Can you just unmute and tell me one by one? And if you can
Sir,
put
it
on,
was worth every second.
okay, okay,
Sir,
okay,
it was very good. It was really
I like very
enjoyable.
much,
Thank you
sir,
so much,
this
sir.
program.
So nice.
Thank you, Professor.
okay.
This is very recently I saw your channel. So
Yeah.
now I am more interested to see more of the YouTube channels you have where you can see
Okay.
a lot of talk on this.
Thank you, sir.
Okay.
I enjoyed very much.
Okay. How was people joining
Sir,
from outside?
2023 is a joyful ending for me, sir, especially.
Okay.
It's a great
Okay.
lecture, sir, because it is a very
You
complicated,
enjoyed it,
complex
Sadatali, right?
theory.
Okay.
Sir, I have a question.
Being a science
Okay.
teacher,
Yeah.
I
I
want
have
to
a
emphasize this.
question, sir.
Yeah.
Excuse
Yeah. I
me,
will
sir.
answer to that question. Yeah. Just a second. So,
Sir, I have
Emmanuel,
a
you were
question.
joining outside India. How did you enjoy? Uh,
It was very great, very 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 interesting.
Amal,
I wish we can
Are you still
continue
there?
to
Amal?
have this all the time.
Okay, fine. So, just quickly, one thing which I need to tell you is that please put up your feedback on this link, which I have just given it. Please copy and paste it. This is a YouTube, just a small video. So, if you can just put up your link, right, that would be great. Okay. Second thing would be that uh, this is yeah. Just a second. Okay, I give this responsibility. Okay. Uh, okay, Monica, can you just do one small thing? I am sending this one, which is a Google form. Okay, this is for the certificate issue. So, Monica, can you quickly click on this and just fill up and let me know that whether it is submitting or not, because I really don't want to miss on anybody's. Yeah, thank you. Happy New Year. I am not done yet. Just 2 minutes more, please. You have waited for so long. So, Monica, can you just click on this and fill up your name, phone number, email ID? I mean, just name, email ID, etc. I just want to know that whether it is coming to as a link, it is working or not. Otherwise, everybody will leave quickly and I will miss their names. I want to know whether it is working or not because I have just opened my Google Drive and I want to see that whether the response is coming or not.
Yes, sir, I'm feeling.
Okay, just fill it and just let me know that you have done with the free. Yeah. Uh,
Sir Shona, thank you so much. This webinar is very interesting.
okay, who is this? Okay, Amal. Okay, so yeah, thank you. You were about to join
Yes,
last time. Yeah, I thought now you're happy.
sir. Uh, sir,
Yes,
can
I'm
you?
happy now.
Okay, just a second. It is working.
Yes,
Okay,
sir,
just
I submitted.
okay. Wait. Let me check. Let me check whether the response is coming or not. Oh yes. Satyam, yeah. It's coming. But where is my Excel sheet? Just a second. Yeah, I got Satyamev, Manan Sharma, Mohammad Sadat Ali, Monica Verma. Yeah,
Yes, sir, it is working, sir.
okay, it's working. Okay,
Can
fine.
you
So
resend the link?
yeah, this is for your certificate. Just fill it up, and not today. Tomorrow morning, as a New Year gift, I will be sending you the certificate. Okay. Now, just one thing I want to tell that Physics for Students, as an organization, along with my wife. Can you, Shubhasri, can you just come in for a second? I want to introduce the new director of this company. We have registered together under the Government of India as MSME segment. Okay, the organization as a whole. But remember, this certificate is not given by Government of India. So I just wanted to make it clear. The organization is being registered, so that is why my lectures, etc., are now much more, made in a better manner because I've got the original registration number, so I really cannot do anything. Okay, so she's in the yeah. So she has also got a master's first class in philosophy, and she is working with logic and philosophy, making papers, etc. So both of us, we are doing that. And another very young woman is sitting. That is my daughter, and she's 13 years, and she's turning 14 years on the 2nd of Jan. That is her birthday. So we are like a family. Yeah, okay. So in order to get those PPTs, don't worry, I am recorded the entire webinar. I am putting it up on my channel. So whatever you want to download, do and just don't delete anything. You can get those PPTs as itself. I will be uploading that on that part. Yeah. So that's it. We are just 2 hours from the new year. And okay, happy birthday to in advance to your daughter. Thank you, Sandipan. So next year, before I take the question, just let you know, next year I have got more plans. January, I am getting somebody called Professor Saumitra, who is actually working on general theory of relativity in Calcutta from Indian Institute of Cultivation of Science. Most possibly on the last Sunday of January, he will be coming to talk more on general relativity, cosmology, career supports, etc. That will be a podcast on my channel, and I will be doing a almost daily class, but I will frame a routine for that: complex analysis, real analysis, general relativity, a lot of other subjects will be coming, tensor calculus. So Monday to Friday I will do that. Only one day I will take a rest, and then again on Sunday. So I'm trying to mix up my videos with my classes. See what happens, to be very honest, videos take a lot of time. I have to frame it, I have to give animation, I have to record it, I have to upload it, and also I cannot explain everything like the way I do, I mean to say, using a Jamboard, drawing those. So classes I think are much better, where you can ask question, etc. So maybe not tomorrow, but day after tomorrow, or maybe from 3rd of January, I will be regular on this channel, Physics for Students, 9:15 to 10 o'clock, and different topics of physics and mathematics. My classes will go on. So happy new year to all of you.
Happy New Year, sir.
Happy New Year, sir.
Thank
Happy
you.
New Year, sir.
Thank you very much.
Happy New Year, sir.
Yes.
Happy
Happy
New
New
Year,
Year,
sir.
sir.
Great year. Look forward
Happy
to
New
see
Year.
you.
Yes,
Bye
sure.
bye.
Mohammed, what was your question, if you can ask me?
Sir, I
Sir,
will ask
I had a
you
question.
in email,
Yeah,
okay?
just a second. Let me answer Muhammad's question. Yeah, tell me. Yeah, Muhammad, tell me.
Sir, my question is that if we move with the speed of light, or if we just suppose that a person has exceeded the speed of light, so will it time become infinite, and will that person can move from one time frame to the another time frame?
No, 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 no. That is, I think, sir, Rajagopal sir can explain. I think with the speed of light, he is talking about the time dilation factor. The time, yeah.
Actually, if you look at Einstein's special theory of relativity, uh, since light has got a, it has been shown by Einstein that light is the maximum velocity in vacuum that is possible for any material object, and
Right.
that can never be reached by any material object. Only the photon is an exception. Photon itself does not have a mass. It does not have a mass at rest. It does not have a rest mass, so it can travel at the speed of light only. But photon doesn't experience time. It doesn't experience time. There's infinite time for the photon. So Einstein's relativity, special relativity is simply based on the fact that light is the maximum in vacuum, is the maximum velocity possible. Of course, there was one Indian scientist, a very famous guy, I think Professor will know better, Dr. E.C. George Sudarshan,
Yes, sir.
way back
Sudarshan.
in
He
the
actually
60s.
disproves that. Right, right. Very controversial.
He talked about the tachyon. Of course, it doesn't violate the relativity principle. I don't know. I have no idea about it. But he has made a lot of stuff, a lot of waves in the 60s. So the tachyon is a postulated particle that travels beyond the speed of light. But then the whole thing becomes a complex. It becomes imaginary. Time becomes imaginary, and all this stuff. So I don't know. It's mathematics is and nobody has found out what the tachyon is.
Right,
So
right.
as of now, relativity, special relativity,
Sir,
is fully established over the last 120 years, and it is the benchmark for all the most of the technology we are using today. And general relativity, for example, GPS is working because of
Absolutely.
because
Yes.
of the time dilation.
GPS is working based on the time dilation.
Yes.
Yeah, absolutely. Absolutely right.
sir,
Excuse
sir,
me,
Okay.
sir, I had a
sir,
question.
I'll recommend
Yes,
a very
tell me.
simple book which I read when I was a
sir,
teenager.
I have a
It's
question.
still there in the market. What is the
Yes,
theory of
tell me your
relativity?
question.
What
Yeah.
is the theory of relativity by Lev Landau? It's still there in Amazon. You can get it. Slightly costly. The very basic. A boy of class 9 and 10 can understand special relativity.
Absolutely. Absolutely. That's true. That's true.
Sir, yes, my question was like as I told you, when we solve that Euler-Lagrange equation for a plane surface, we get a straight line. What happens when we solve it for a curved surface?
Uh, I will answer to it a little bit later, because this is out of the discussion of today's webinar. You let me know. I will definitely tell you that whether you get a function in a straight line or you get a curvature, right? That is what your
Yes,
question.
yes, yes, sir.
I'll
Yes, sir.
let you know on that. Okay. Anyway,
Sir,
I'll
where
go.
can we
Yeah.
contact you? Where can
Uh,
I contact you?
you have got my phone number, my WhatsApp number 9830219677.
Yes, yes, yes,
Yeah,
yes,
that is
yes,
the
sir.
one plus my email ID. Okay, so I would request that it was a very long webinar, and I am equally thankful to all of you that you have participated and those who stayed. 32 people still were staying long. Please put up a feedback, honest feedback. I would wait for everybody's feedback on this link. Rajagopal sir, I would earnestly wait for your feedback.
Sure,
So whatever,
sure.
take your time and put up an honest feedback from Sagar and Satyamev also, because these feedback actually gives a lot of motivation. As you understand, I am a very small YouTuber. I don't have a millions of subscribers because Rajagopal sir, you understand that these things won't go beyond like a food blogger or something. My only intention for these 2 long hours, all this preparation, and it takes a lot of time because I have to make shorts every week. I myself feel very frustrated that I am conducting, why I have to tell. But maybe with your blessings, one day will come when all people, without telling, they will know that I am conducting a webinar. So it takes a lot
Sure.
of time, energy, etc. But the only intention is to share this because I am not boasting. It is not my ahankar, but I can tell that this type of webinars every month repeatedly, I have not seen on YouTube. It really happens. A very long discussion on general relativity. There are very good videos, etc. But I mean to say, I want that this light to be spread across the world wherever you're located, so that we can more people can be actually benefited from this kind of a webinar. So earlier I never used to record, but now I am recording because maybe Sagar or maybe even Satyamev at one point of time think that let me go back to this point and let me read something. So how will you do that, right? So it is better that you have a video and you can do and share that video. And next time I can tell you, when I'm doing the same general relativity, I will change certain areas because maybe I put a little bit more stress on just theorem next time, maybe a little bit on differential geometry also. The reason is that this is really huge. This is really huge. You cannot make everything in one. So slowly, step by step, things will come up.
So,
Okay, so there are a lot.
sir, where
Raja.
to fill the feedback form?
Okay, I am giving it to you. Wait. Certificate form. This is for your certificate.
No, 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 not certificate. Feedback
Okay.
form.
Oh, feedback. There is no form actually. I am giving this link to the chat box. You click on that video, and in the comment box, just write your feedback,
Okay,
Raja.
okay, okay,
That's it,
okay,
right?
okay. Right.
And
Yeah,
for the
thank you for this
certificate, this
nice
is
lecture.
yeah, thank you. So I would like to take a leave. I am also feeling tired for 2 hours long. As you understand, it is a lot of energy, etc., and lot of presentations, etc. Thank you very much. Wishing all a very happy new year. Thank you, Raja Gopal sir,
Thank you, sir.
especially for such staying for such a long time.
No, sorry. Thank you. My pleasure, sir. Thanks a lot. Namaskar.
Thank thank you. Thank you very much. Wish you a very happy new year. Please do put up your comment. Please fill up the certificate form, and I will issue the certificate by tomorrow. And do share
Okay.
it and be there with me through my journey. Thank you, Monica, and thank you all the people from India and abroad. Thank you very much. Wishing
Thank
you a
you,
Thank
happy.
you,
sir.
sir. Thank
Yeah.
you, sir. Happy New
Thank you,
Year.
sir.
Thank you, sir.
Goodbye.
Thank you, sir.
Happy New Year. Good night, sir.
Good night.